1.4, properties of RISC architecture. Still, this one we can treat as a summary because most of the properties we have learned before. Yeah. So we just go through those main properties. Yeah. Probably we add a little pieces, a few more new items. Yeah. Yeah. Key properties of RISC architectures. Yeah. Because RISC, we know it's a big class of architectures. Inside the RISC, ARM, MIPS, ARM, right? Still also there are other RISC architectures. It's a big class of architectures. Yeah. All right, but they share some common properties. Yeah. So let's look at these basic common properties. All operations on data apply to data in registers. Yep. Yep. All operations on data. Yeah. Operations, yeah, we need to use some data, right? Yeah. So apply to data in registers. Yeah. Not data in memories, right? Yeah. So that's the one. Yeah. Hope you know, because we saw several before. Yeah. All operations on data apply to data in registers, not data in memory directly. That's the meaning. Okay. So that means if you have data in main memory, we need to load them. We need to load those data items into registers. Then we apply our operations on those data items in registers. That's the meaning. Okay. And typically change the entire register 32 and 64 bits per register. Yeah, here, let me explain the second half of the sentence. All right. 30 to 64 change entire register. Yeah. So not half, right? You remember half. Yeah. Sometimes remember when we talk about floating point, right? Half. Yeah. Part. Yeah. So here, because the RISC emphasizes simplicity and performance, so it does not use one whole register to store multiple pieces. Yeah. Only for one piece of data. Yeah. So every time we apply operations on it, we apply on the whole register, not part of it. So that's the first property. Second, the only operations that affect memory are load and store operations that move data from memory to register or to memory from register, respectively. Yeah. Load, store, copy data, load from memory to registers, store from registers to memory. That's the only operations that affect memory. Read the right. Yeah. Affect. Yeah. Affect. Yes. Yeah. Probably more precisely, access, right? Affect. Do you mean affect? Do you mean change, right? Yeah, because read, no change, right? Yeah, write operation change. So if your affect means change or not, the question. Yeah. But we know we need to do both read and write operations. Yeah. All right, anyway, so you know the meaning. Yeah, here. Next one, the instruction formats are few in number. Instruction formats, yeah, field in number with all instructions typically being one size. Yeah. Fixed. Yeah. Here. Yeah. But here, yeah, this probably a little special here. Yeah, let me, yeah, because here, typically, yeah, being one size, right? Yeah. The reason is very simple. We know RISC, this big umbrella, covers large number of different smaller RISC type architectures. Some of them, most of them use the fixed length instructions, but there is some small variation. So that's why it uses this typically. For example, the ARM, we know, the cell phone ARM. Yeah, this one, it used the mixed instructions, two different lengths, one 32-bit instruction, another 16-bit instruction. Okay, yeah, variable length. Yeah, for some reason, for some special reasons. Yeah. So that's why, yeah, it said, all instructions typically being of one size, but not 100, not all in one size. There is some exception there. Yeah. All right. So next one, properties of ALU instructions. Main properties. Take either two registers, two types. The first one, two register version, or a register and a sign extended immediate as two source operands. Here we're talking about source operands. Okay, operate on them. Yeah, source. We apply operation on them, on those two source. Yeah, the source, there are two different types. One both from registers, one from register, another from the immediate field. Yeah, case. Yeah, and store the result into a third register for the first case, or a second register for the second case. Yeah. So we saw many examples, so we know what's the meaning here. Yeah. So I do not need to, write two examples out for this property. Yeah. Another one. Yeah. Typical operations include add, subtract, and logical operations which do not differentiate between 32-bit and 64-bit versions. Yeah. Here the meaning is this. Yeah. Here we're talking about integer operations. Okay. Here, do we talk about integer include? Yeah. Yeah. Integer logical. Do not differ. Yeah, here, yeah, we may not. Yeah. Anyway, integer or floating point. Yeah. So we contain both. Both do not differentiate between. Yeah. So that means for these two versions, the instruction length both 32. Even the details the same, not differentiate. Yeah, because the difference of 32-bit, 64-bit, the difference is only at address sense. It's 32-bit, 64-bit, right? Other than that, instruction content the same. So that's why do not differentiate. That's the meaning. Okay, yeah, all right. Yeah. Then, in maps, there are both signed and unsigned forms of the arithmetic instructions. Yeah. Yeah, so this one, simple, yeah. All right, yeah. We saw examples, yeah. Next, group of properties. Properties of load and store instructions. Yeah. Summary. Yeah. Here. Take a register source and an immediate field as operands. Immediate field corresponds to that displacement, right? Yeah. Or offset, sometimes we call. Yeah. The sum, yeah, sum, yeah. You add displacement plus the base address, right? Adding together, sum called effective address. Effective address. Yeah. Remember, in one of the questions, comprehension questions or quiz questions, probably comprehension questions, I use this term, effective address. So I put in the parentheses, so the actual address. So after you add those two numbers, you get effective address. The sum, called the effective address of the contents of the base register and the sign extended offset. Offset, remember 16-bit. 16-bit, you cannot work on it directly. You have to extend it. Two possibilities. One, extend it to 32 bits. If your address space is 32-bit. Or another possibility, extend it to 64 bits if your address space is 64 bits. All right. So that is for this property, as the memory address. The next property, in the case of a load instruction, a second register operand, first, second, right? So, try to imagine that. So if I write example, that's very easy. Load R2, comma, here we need some, displacement number, R1, right? Things like that. First, second, okay? All right. So here, look at that. A second register operand, this one, acts as a destination. So we call destination field, right? Last video. Acts as the destination for the data loaded from the memory. That's this case. The next one, in the case of a store, so let me write a store version. R2 still, let me use R1. Now, here, the second register operand is the source, RT, okay? RS, RT, both RT. Here we also use RT, okay? But this RT is source. We retrieve data from that location, so that's the source. This RT is the destination. Okay, and it's a field, right? So destination, but also it is a field. All right. That is stored into memory. So that's the difference. Okay, the summary. So we discussed this, kind of comparison before. The last property. So the last property. When the instructions load a double word and store a double word, load or store the entire 64-bit register content. Here. For simplicity, right? So RISC, for simplicity, So do not try to split, okay? Do not try to split 64-bit register, for multiple operands. Do not try to save space, because you add a lot of complexity to it. Here you can see in several different places we emphasize this special rule. Yeah. All right. Yeah. But this last property for this group. Yeah. We have another group. Yeah. The last group. Branches. Yeah. Properties of branches and jumps. Yeah. Branches are conditional transfers of control. Yeah. Yeah. So there are usually two ways of specifying the branches condition in RISC architectures. Yeah. All right. The first one with a set of condition bits, sometimes called condition code. Yeah. Or by a limited set of comparisons between a pair of registers or between a register and a zero. Yeah. So we are familiar with this one, right? In our example, we talk about that, but we didn't talk about the first case. Yeah. First case, that, yeah, but we do not have specific example for it. Yeah. So we do not discuss for it. Yeah. All right. So then MIPS uses later. Yeah. So MIPS uses this. Oh, that's the possibility. Yeah. The MIPS, we know MIPS is the special RISC architecture. Yeah. MIPS use the later. Yeah. And we study the MIPS architecture as the case study. Yeah. And the RISC, for other RISC, we do not have time to study. Yeah, actually, even we have time, but too complicated. So even we have time, we won't study other types of RISC architectures. Yeah. All right, the last one. Yeah, so not the last one. Yeah, but second to last. In all RISC architectures, the branch destination is obtained by adding a sign extended offset to the current PC. Yeah. Offset plus the PC. Yeah, we know the meaning. Stored inside that PC. Temporary register. Yeah. All right. The last one. Unconditional jumps are provided in many RISC architectures. Yeah. All right, so that's all we need for part D. Yeah. And after that, our last part, part E, yeah, the reason I need to go another part because it is so important. Part E, we will talk about pipelining technique. Yeah. So I hope we can cover the main properties or the structure, the algorithms related to the pipelining technique. Yeah. Then we will, complete, everything I like to cover for this semester. Yeah. But for those students who are interested in PhD here, for qualifying exam, I will do another module. Yeah. But for that part, I can use later time. Yeah. So when you work on your final, yeah, next week I will post the final. When you work on your final, I will record that part. Yeah, for PhD, students interested in PhD program. Yeah. All right, so let me